let's look at a more realistic kind of implementation and touch on the trade-offs of these different platforms and QPU implementations. So as I mentioned before, these QPU platforms have very different physical properties. They operate at different regimes of control and the electromagnetic spectrum that actually drives these qubits. So, for example, superconducting qubits operating in the microwave regime, whereas neutral atoms, color centers, trapped ions, these matter-based QPUs operate in the near infrared or visible wavelength regime. So different QPUs operate at different wavelengths. So already at the lowest physical level, we already have a mismatch and a need to harmonize these different technologies. Again, in this quantum data center, each QPU will have a quantum network interface card or quantum interconnect. This allows it to connect the QPU to the rest of the network, ideally over an optical network. So by bringing in the concept of optical frequencies and light in general, we start to build in a common language, a physical medium by which all of these QPUs can communicate. So what does a QNIC consist of? It consists of these interconnects. Depending on the QPU platform itself, these interconnects will look widely different. So we have the notion of transducers. So these components are responsible for converting this the microwave regime that, say, superconducting qubits operate at, and making sure it can operate at optical. So it has microwave to optical transduction and vice versa. There are many ways to build these transducers, but it is a big engineering challenge. Different kinds of resonators you can use to build this. For the visible and near infrared spectrum, the frequency gap and energy gap is not as wide. So we can have frequency converters and optical converters that are say less of an engineering challenge to bridge that gap. We also have the notion of potentially using photon sources themselves to carry out this interconnect process, especially dual wavelength sources that can spit out an entangled pair of photons, one at which is compatible with a certain QPU platform, and the other being more compatible with the optical quantum network. So different ways of building these network interface cards. So and you see this common theme, right? Each QPU platform lends itself nicely to certain kinds of technologies and also encodings. So there are different ways to encode entanglement and our qubits in light. I mentioned time bin, polarization, frequency bin, and spatial or path encoding. So oftentimes there's a certain encoding of light that lends itself really well to the network interface card that we're talking about. So we started to introduce this common language of light and optical frequencies, but now we still have some kind of difference and modality specific encodings that we also need to harmonize. So that's where the role of the rest of the quantum network fabric kind of comes into play. So it's responsible for harmonizing these different photonic qubits to make sure we can convert between these encodings. We also need switching and routing capabilities to make sure our flying qubits are being routed to the right places and the right communication qubits on the QPUs. I mentioned the role of a quantum memory bank earlier as a very useful device or component to have in the network to buffer our quantum states, to use it for synchronization, for storage, and it's just a very useful tool in the network. We have multiplexing technologies we can use to increase efficiency and rates of this entanglement. And we also have the Bell state measurement arrays. So these technologies are, again, responsible for carrying out that photon interference, which can result in entanglement generation. So many architectures for the quantum data center will consider this array of photon detectors and interferometers to carry out Bell state measurements. So the rest of the QN fabric, the quantum network, will have these components in some form. There are different ways of architecting this depending on the scale we're talking about, depending on the QPUs that actually will be working together. But generally, this gives a flavor of all the stuff we need to integrate these QPUs not only with each other, but with existing infrastructure.